Okay, in the following slides, we will introduce the basic idea of images. How does an image construct? So how do we describe an image? And what kinds of characteristics can be extracted from images? So basically, this information, the data of the following slides are basically from the chapter 2 and chapter 6 of the digital image processing textbook. This is a very uh, typical textbook for digital image processing course. So if you have already taken the digital image processing course, you may be able to quickly screen or quickly browse the following slides. That would be okay. But for the students who haven't taken digital image processing, here are some basic introductions for you to quickly understand the characteristic of images. So here we will first talk about how does a digital image construct. Okay, we human beings live in a analog world. Okay, so everything here in the real world is a continuous signal. Okay, and for digital images, we have to store the image information in computer with finite numbers of data. Okay, so we cannot store infinite amount of data or infinite amount of information. So we have to digitize the real world object into digital images so that we can store it. Okay, and in the real world, how can we see an object? How can we do that? That is because there is a illumination source like the sun, and the light emitted by the sun emit to the object, and the surface will reflect part of the sun, part of the light. Okay, and according to the characteristic of the surface, some light with some wavelengths will be absorbed by the surface, but some light with another wavelength will be reflected. Okay, and this kinds of light enter into our eyes so that we can perceive. Okay, there is an object in the real world. For the imaging system, the imaging system is like our eyeball, our vision system, and the imaging system collect the incoming energy and focus it onto an image plane. So there, in the digital camera, there is an array consisting of a grid of image sensor, so that each image sensor can sense the intensity of the light. Okay, and just taking the gray level image as an example, for the pixel who receive higher intensity, brighter pixel will be stored. Okay, so when the sensor sense the incoming energy, before storing into the computer, we have to conduct two digitized process. The first one is sampling. The second one is quantization. So we will talk about the details later. And for each sensor, we may receive different degrees of intensity, so that we can store different intensity value. Okay, and for each image sensor, the basic unit to store the image component is called pixel. That is a picture element. That stands for picture element or image element. Okay, so based on this imaging system, we can transfer an analog object into a digital form. Of course, you can see that there may be not exactly the same. Okay, the analog things and the digital thing may not be exactly the same, but by increasing the resolution of the image sensor, we may increase the resolution of the digitized image. Based on the imaging system mentioned above, we can represent an image by a 2D function. So for each image sensor, the perceived intensity may be from 0 to infinite, and the intensity value of the pixel located at x, y is denoted by the fxy. Okay, and actually, the perceived intensity value can be characterized by two components. The first one is determined by the illumination source. That means the degree of light, the intensity of light emit to the location x and y. So this is called the IXY, and this value may be from 0 to infinite, depending on how the illumination source emit the light. The second component is called the reflection factor, and this means the proportion of the light reflected by the source, by the surface of the image object. So this factor is determined by the characteristic of the imaging objects, and the value would be from 0 to 1. When the RXY is 0, that means all lighting energy is absorbed by the object, so no light will be reflected by this object. In this case, we will perceive that this pixel is black because no light has been reflected from this point. And for the reflection factors equal to 1, that means all light of different wavelengths has been reflected by this point. So we may perceive that it is in white. This pixel is in white. Okay. For image sampling and quantization, these two processes are very important to digitize an analog signal. So the previous formation model, fxy, is a continuous value, but actually in computer systems, we cannot store continuous value. So we need to digitize them. Okay, so the first digitization step is called sampling. So we can see that assume there is a continuous object here, and if we just focus on this axis, this horizontal, this row, okay, and we can expect that, okay, first this is white, so so high intensity value will be obtained. So here we can see that, okay, these pixels are in high intensity values, and at the boundary between the background, the white background, and the black object, so the intensity value drop abruptly, and then from the left to the right, the intensity value gradually increase and then gradually decrease. So here we see the intensity value increase and decrease, and then when we go outside the object, we go into the white background, so suddenly the intensity value increase to the highest value. So here is the whole continuous value, but we cannot store such continuous signal. So the only thing we can do that we just sample a few of that. So here we may equally sample, for example, for every 5 image sensor, we just store the value. So here we store the value here, we store the value here, we store the value here, here, and here. So we cannot store every value in this continuous signal, okay? Because there are infinite numbers of data we have to store. So this is impossible. And for quantization, that means even we just have finite numbers of sample data, we cannot store this value in infinite precision. Okay, in infinite precision. That maybe, for example, this value may be an infinite number that will be maybe 3.14, 1575, and so on. Okay, but we cannot store numbers like this, so we have to quantize the real value numbers into just a finite set of numbers. So we can see that all these 4 sample points may have different intensity value, but after quantization, we just store it as a fixed value. And actually, these values are more appropriately represented by computer system. Okay, so the quantization means we cannot store values in infinite precision. So we just store it, we just quantize it into finite set of number. Okay, so by sampling and quantization, we can transform a continuous signal into finite set of digitized discrete number. So here is an example. The original object is looking like this. So this is the analog objects, and we can see that it gives rise to a continuous signal. But based on image sampling and quantization, for each image sensor, we just sample it. Okay, we cannot store every number. Okay, so we just sampling a set of name, and the frequency of this sampling depends on how we arrange our image sensor. Okay, if we have more image sensor in a finite unit area, we will get higher resolution. Okay, and about quantization, we have to decide for the intensity value from the lowest intensity value to the high intensity value. We will use how many bits to represent the intensity value. Okay, so this determines the quantization level. Okay, so here is an example. We can see that for each image sensor, we store 1 pixel, and for each pixel, we may store the quantized intensity value. And we usually store an image by a matrix in computer system. So we can see that these are the quantized value. Okay, and this is the image formation model representation. We next introduce some common terminologies used to describe the characteristic of digital images. The first one is dynamic range. Dynamic range is defined as the numbers of discrete gray level allows for each pixel. As I said before, how do we represent from the lowest intensity value to the highest intensity value? So how many levels do we try to describe the difference between the lowest to the highest? Okay, so the numbers of gray level allowed for each pixel is defined as the dynamic range. And due to processing, storing, and sampling hardware consideration, the numbers of gray labels typically is an integer power of 2, like 2, 4, 8, 16. And the most commonly used dynamic range is 260, 256. That is equal to 2 powered by 8. Okay, and we refer to the image whose gray label span a significant portion of the gray scale as having a high dynamic range. So in the following 3 images, which one do you think to have the highest dynamic range? Okay, the answer would be the second one, because in the second image, the brighter pixels are very bright and the dark pixels are very dark. So basically, the difference between the brighter one and the darker one will be large. In the contrast, the left image, almost every pixel are bright, and in the right pixel, almost every pixels are dark. Okay, so basically, high dynamic range images often present high image contrast, and we can see more details in high dynamic range images. And basically, the technology of high dynamic range images is still an ongoing research topic. The next one is the image size. Okay, and for a square image with width and height as n, the total numbers of bits required to represent the image would be n squared times k. N squared times k, where n is the image width and height, and k would be the numbers of gray label. So here is a table showing how many bits are required to represent images of different sizes, like to represent a 32 by 32 images. And if we allowed 16 gray labels, then we will need more than 4,000 bits to store this image. And for a 512 by 512 pixel image, if we allow 16 gray labels, we will need these kinds of bits to store this image. Okay, this is quite reasonable because when the image is larger, we need more bits to store this image. Another terminology is called the resolution, especially the spatial resolution. So basically, sampling is the principal factor determining the spatial resolution of an image. So for the same object, for example, this flower, if we put our image sensor more densely, then we can have higher resolution digital image. So here, this image is a 1024 by 1024 pixel image, and here is 512 by 512 image, and we can see that basically the image content is the same, but we can see more detail in the larger image. So basically, higher image of higher resolution present more detail, and of course it convey more information. So this is the so-called spatial resolution And you can expect that image with higher resolution require more bits to store. So if we artificially enlarge a small image to to a larger one, so we artificially enlarge it. How what kinds of image can we obtain? So here we compare that. So this image is resampled or enlarged from 512 by 512 to this size. And we may see that, okay, the visual difference between these two images may be so subtle. But if we enlarge 64 by 64 image to 1000 by 1000, we can clearly see the stagger effect, the blur effect. Okay, and this is quite reasonable because in the original 64 by 64 image, they just convey just a little portion of the visual information. So if we artificially enlarge it, we actually don't increase the information. We don't increase the detail of this object, so that we get a blur image. So here is the gray level resolution. The previous one is the spatial level. Here is the gray level resolution. That means the numbers of gray labels we use to represent each pixel. So here is the image that for each pixel they may have 256 gray labels. Okay, and here 128, here 64, and so on. And we can see that, for example, in this image, the gray label will be quantized into 4 different. Okay, so the intensity value will be quantized into 4 different labels. So we can just represent 4 different intensity. And if we just use 1 bit to represent a pixel, we just can describe whether this pixel is white or black. Okay, so we can just see a black and white image. So this is the so-called gray level resolution. The next important thing is histogram. The histogram of an image with gray label is basically it's a distribution indicating how many pixels are with a specific gray label. Just like this, we can see that a histogram can be represented like this. HRK is equal to NK. Here RK is the case gray label, and NK is the numbers of pixels in this image having gray label RK. So this is the so-called intensity histogram. And we can give you an example here, like if we have an image here, maybe just 4 pixels, and for example, this pixel is intensity value 100, and this is 50, and this is also 100, and this is 60. So to construct the intensity histogram, we just count the numbers of pixels with we can see that we have 1 pixel with intensity value 50. So here about the 50 intensity value 50, there is a 1 pixel, and for the we have another pixel with intensity value 60. So here we have the 1 pixel, and we have 2 pixels with intensity value equal to 100. So we have 2 pixels here. So here is a very simple distribution indicating the numbers of pixels having a specific gray label. Okay, so this is the so-called intensity histogram. And when you use the histogram in the future, remember to normalize your histogram. The reason to do normalization is, okay, we usually have to compare images of different size. For example, we have a small image here, and we may have a large image here. And for the smaller image, because the smaller image has much fewer numbers of pixels. So for example, half of them is 100 and half of them is 50. So we can see that, okay, at 100 we have 2 pixels, and 50 we have also 2 pixels. But for the large image, if we have 16 pixels, and we also have half of them 100 intensity and half of them 50 in intensity. If we can construct the histogram, we may have this 100, and here is 8 pixels. And for 50, we also have 8 pixels. But here we only have 2. But for human beings, we can see that actually these two images are quite similar, because the intensity distribution is basically the same, but the numbers of pixels having a specific gray label are different because of the size, the image size. But if we can do normalization, we can construct a histogram like this. We divided the numbers of pixels by the total numbers of pixels in this image. So basically 50% of the pixels in this image have intensity value equal to 50, and the 50% has intensity value equal to 100. And by normalization, we also have the same distribution like this. So remember, when you try to compare different images, remember to normalize your histogram. So here are some examples showing 4 different images and the corresponding histogram. So you can see that from the first image, basically almost every pixels are dark. So here, for the dark image, the intensity histogram, the value will concentrate on the left part of this histogram. For the bright image, almost all pixels concentrate on the right part of this histogram. And for low contrast image, so almost every pixel are gray. Okay, they are all gray. So the intensity value will concentrate on the central part. And for the high contrast image, so the so-called high contrast image is that brighter pixel are really bright, darker pixel are really dark. So in high contrast image, we will have a histogram like this. We have pixel with very high intensity, and we also have pixel with very low intensity. So according to the histogram, we can expect the visual effect or the statistical characteristic of different images. Okay, so this is why we can utilize histogram to do some image processing, like image enhancement, image compression, and image segmentation. So if we try to enhance the contrast of this image, the most intuitive way is we just transform this histogram to this histogram. Okay, we just make the distribution more spread so that we can obtain higher contrast image. Okay, so if you have taken the digital image processing course, the image enhancement or image segmentation would be one of the homework you have to do. In previous slides, we take the gray level image as the example to show the image characteristic and intensity histogram. Now we go to colorful image. Okay, and we first introduce the idea of color. So basically, each color can be seen. That is because the nature of the light reflects from the object. So for the light from the sun, for example, actually it consists of many lighting energy with different wavelengths, and the light with different wavelengths may be perceived in different colors. So we can see here from these images, and when we were in the high school, we have already knew that the famous scientist Newton, he used an optical prism to separate the white light into colorful light with various wavelengths. So after more investigation and study, we have known that the white light is a mixture of various light with different wavelengths. And if we see the color spectrum, the x-axis is the wavelength from the shortest wavelength to the longest wavelength, and we can see that light can be represented as a wave, and with different wavelengths, different colors can be perceived. And we human eyes cannot perceive very short the light with very short wavelengths, and cannot perceive the light with very long wavelengths. And the color range we can perceive is in the visible spectrum. So these colors are called visible colors. And from the shorter wavelengths to longer wavelengths, we perceive dark blue to green to yellow to orange and to red. And for the very short wavelengths, we perceive ultra violet, and for the very long wavelengths, we perceive the infrared. Okay, and basically here is the whole spectrum of the color. So we can see that the X-ray is actually a light with very short wavelengths, and the infrared and the microwave are a light or wave with very long wavelengths. So here is why we can perceive different colors. Okay, that's totally depends on the wavelengths. And we humans can perceive light because we have a photo sensor, we have image sensors. Now, basically, the neuron of our vision neuron can be divided into two categories. That they are rod and cones, depending on the shape of depending on their shape. And basically, rods are used to perceive the intensity of light, and the cones are used to perceive different color. And basically, cones can be divided into three principal sensing categories. One category is sensitive to shorter wavelengths, that is, they are more sensitive to blue. And one category is sensitive to middle wavelengths, that means the green, they are more sensitive to green light. And another category is more sensitive to red. Okay, so that's why when we design hardware to present color, we usually use the intensity of or the strength of red, green, and blue to represent a color. And due to the absorption of the human eyes, colors are seen as a variable of three primary colors they are red, green, and blue. And approximately 65% of all cones are sensitive to red, and 33% to green, and only 2% is sensitive to blue light. And the difference between different ratios of cones, that may be due to the evolution. Some scientists think that our vision neuron less sensitive to blue were just involved in the recent maybe million years. So only 2% of cones are sensitive to blue light. And basically, colors or light they have several characteristics. The first one is different light with different wavelengths can be added together, and we human can perceive as a mixture of these two light. For example, magenta is actually red plus blue. Okay, so magenta, if we add red and blue, we perceive magenta. And the sign is equal to green plus blue, and yellow is equal to red plus green. Okay, and this is called the secondary color of light. And the primary color of pigment subtract a primary color of light and refract the other two. So we mentioned about the mixture of light. So that's additive primaries. And when we talk about the pigment, when we print pigment on white paper, okay, for example, when we print the yellow pigment on a white paper, why we can perceive yellow? Okay, so basically the paper does not emit light, so we perceive yellow. That is because there is a luminous source emit white light on this on the paper, and because of the pigment, this pigment absorbs blue light, and it reflects red and green, so that red plus green make us perceive yellow. So this is the concept of subtractive primaries. Okay, so remember, when we print, for example, when we print cyan pigment on paper, that does not mean that this region emit cyan light. No, that is on the opposite. The cyan pigment actually absorbs red light, so it reflects green and blue to make us perceive it's a cyan. So this is quite important when we design the printer. And in addition to red, green, and blue, we have another way to present or to describe a color. So usually we may also use brightness, hue, and saturation. The brightness represents the intensity value. That is also the strength of the light. Okay, and hue is hue totally determine the color as perceived by the human. So red, green, blue, yellow, okay, that's all determined by the hue value. Saturation means the relative purity of the amount of the white light mixed with a hue. So for example, we may get a red hue, and according to the purity, we may perceive different kinds of red. For example, if the purity of this light is not so high, so it has more mixed with the white light, so we may perceive pink. Okay, so pink basically is red. It's kind of red with low saturation. Okay, so less saturated color like pink is basically red plus white. So we can see that pink is a low saturated red, and the lavender is actually the violet plus white. So lavender is a kind of low saturated violet. And basically, how we the color we perceive depends on hue and saturation. So hue and saturation taken together is called chromaticity. Okay, so that's why we perceive the color, and the strength of the light is depending on the brightness value. So in computer system, how can we describe a color? So basically, according to the foundation we described above, we have to specify the amounts of red, green, and blue to describe a particular color, and so that we need three stimulus value that are jointly called the tri-stimulus value, and we denote it as X, Y, and Z respectively. So a color is then specified by its trichromatic coefficient that is defined as actually the normalization version of X, Y, and Z. So you can see that the small x is basically the normalized capital X, and then the small y is basically the capital the normalized capital Y, and so on. And small x plus y plus z is equal to 1. Okay, so we can use xyz, normalize xyz to specify a color. And using the CIU chromaticity diagram, we can show the color composition as a function of x and y, because when we specify x and y, we have already specified z, because z is equal to 1 minus x minus y. Okay, and the CIE is an organization that specify color specification. So here you can see a figure that all the visible light can be represented as the combination of x, y, and z. So here you can see that this is x-axis, this is y-axis, and because specify x and y already specify z, so we don't show z here. And you can see this region is not a square region. That is because not every combination of x, y, z can be seen by human. So here, for example, when the x is 0.5 and y is 0.1 and z is 0.4, such color cannot be seen by the human. So here we only show the visible color region, and we can see that um, for any color we can perceive can be described as a combination of X, Y, and Z. For example, the white value, the white color, can be specified as X is equal to more than 0.35, and the Y is specified as around 0.4, and so on. Okay, so we can see that this is why we define the white color. Okay, and when we want to specify the green, pure green, then is we can specify X like this and Y like this. Okay, and so this is the surrounding this region is actually the pure red or pure gold. Okay, and all others, and the corresponding wavelengths. Okay, so here we can see that the point mark green has approximately 63% of green, 25% of red. Okay, and the composition of blue is approximately 13. So here, this is the according to many experiments and how we perceive the color, and they do a lot of statistics to show that when we the perceived green is actually a combination of these three tri-stimulus values. So the previous two slides showed how we physically or psychologically perceive color. So in computer system, how do we exactly describe a color in a discretized value? Okay, so here we call it the color model or the color space. A color model is a specification of a coordinate system and a subspace within the system where each color is represented by a single point. So we define a coordinate system, and every color is a single point in this coordinate system. Okay, and for computer system or computer related system, we have already designed many color space or many colors. For example, for the hardware oriented or application oriented, or according to the application, we may select one of them to represent color. For example, the RGB color space. Okay, that means we specify a color based on the value of, based on the strength of red, green, and blue. This color space is usually used in color monitor and color video cameras. And actually, this is the most basic color model. That is because we already said that our cone can be divided into three categories that are more sensitive to red, green, and blue. So that's why the RGB color model is usually used first. The second one is the CMYK color model. That is cyan, magenta, and yellow. And this color model is usually used in color printing. Usually using color printer. Okay, and you may also know the CMYK color model. That is CMY plus black. Okay, because we know that when you want to print the black color, if you use the CMY color space, you have to print cyan, magenta, and yellow so that the pigment can absorb all the light, all light with all visible wavelengths. Okay, with all wavelengths, and that would be quite expensive. Okay, so after some experiment, the industry also invent the black pigment. So when we print the black pigment on paper, uh, this portion can absorb all light, so that we can perceive that uh, it's a black region. And also there's another very popular color space called HSI or called HSV. That is hue, saturation, and intensity. As we mentioned above, we can specify a color by the hue value, saturation, and intensity. And actually, HSI color model is more closely matched with human perception. Okay, so we will describe it later. So first, we introduce the RGB color model. So here it's based on a Cartesian coordinate system. So we specify 3 axes that is corresponding to the strength of red, green, and blue. Okay, so by specifying the 3 strengths corresponding to RGB, we can specify any visible color. So different colors are points on or inside the cube. Okay, so basically RGB color space is a cube, and here if we have the highest strength of red color channel but with 0 intensity on green and blue, then we may perceive red. Here we perceive green, here we perceive blue. So the right one is the corresponding color cube. So red, green, and blue. And as we said before, when we plus red and green, so here is 1, 1, 0. So if we plus red and green, we got yellow. If we plus red and blue, we got magenta here. Okay, and if we plus the highest strength of RGB, we got 1, 1, 1. That is white. So that's how we represent a visible color inside the RGB color cube. So here is another example. If we specify the intensity of red, green, and blue, and here this is not actually gray. So this is we use the intensity value to specify the strength of gray. So basically, if we specify all colors, all pixels with the same intensity of red, and then on the right side we have high intensity on green, on the upside we have high intensity on blue, and we jointly combine them. So we can see that on the right border, because of the high intensity on green, so we perceive green, and because on the bottom side we have pure green, and on the right top side, the right top corner, we have a mix on green and blue. Okay, so we got cyan here. Okay, so here is the combination. You can see that this is an example by combining different settings of RGB. Okay, and if we specify the R equal to 0, so for example, if we specify here all 0, then we got a color plane like this. If we specify G green to 0, then we got a color plane like this. Okay, so can you imagine why? Because here we have for example, here this corner we have a red equal to 127, and we have green 0, and here we have blue 0. So here this point is actually 127, 0, and 0. So actually this is a gray. Okay, this is a red pixel. Okay, and you can imagine another color plane. The CMY and the CMYK color model are usually used in printer, and as we mentioned above, the CMY and the CMYK are the subtractive primary colors. So when the surface coated with the cyan pigment, and it is illuminated with the white light, no red light is reflected from the surface because of the pigment absorb red light, so it just reflects green and blue, so we just perceive cyan. Okay, so this is the subtraction concept. And most devices that deposit a color pigment on paper require CMY data input or perform RGB to CMY conversion. So when we want to print a colorful image on paper, so a colorful image can be seen on our color monitor, and our color monitor uses the RGB color model. Okay, and but when we transfer this information to the printer uses the CMY color model. So we have to do a color space transformation, and basically such transformation is quite easy because their relationship is quite easy. It's linear, and basically that's just a subtraction. So CMY is equal to 1 minus RGB. Okay, so assume that we have already represent the intensity of RGB. We have normalized the intensity of RGB from 0 to 1. So 1 minus R is C, 1 minus G is N, 1 minus B is Y. And then we can use such color conversion formula to transfer RGB color model to CMY color model. So RGB and CMY color system are more suitable for hardware implementation. Okay, RGB are usually used in a monitor. Okay, and RGB system match nicely with the fact that our human eyes is strongly perceived to red, green, and blue. But RGB and CMY are not well suited for describing colors for human interpretation. So this idea is quite important. Although our cones can be roughly categorized into 3 types, but our human brain does not actually perceive color by the combination of red, green, and blue. Okay, based on many psychological experiments, the psychologists say that our human human interpretation on color are basically based on hue, saturation, and intensity. So we describe a color object by its hue, saturation, and intensity, or sometimes we call it brightness. So intensity or brightness or value basically are all the same. Intensity, value, or brightness are all they all mean the intensity of light. Okay, so as we mentioned above, hue is the color attribute that describes a pure color. Saturation is the degree of pure color diluted by white light, and the bright is basically the light, the strength of light. And an HSI color model. Why this color model is important? Because this color model decouples the intensity component from color carrying information. In RGB color model, there is a problem. When the R value getting large, the G and the B value also usually getting large. Okay, so we say that these 3 color channels are not independent, but in HSI color model, I value is independent to S and H, edge is also independent to the other two color channel. This is quite important when we try to develop some multimedia application. For example, compression, image compression. Okay, the correlation is a very important step in image compression. Okay, so if you have taken data compression course before, you may understand this. So how do we describe an HSI color model? So basically, we can imagine that we can take the RGB cube and stand on the black vertex with the white vertex above it. So we just use the same cube, but right now we rotate this cube to make the black vertex stand, and the white vertex just above it. So we just use another viewpoint to see the cube. And when we look this cube on top of this cube, and we can see that it's actually a hexagon, and in the counterclockwise rotation direction, we can see the red, yellow, green, cyan, blue, magenta, and then return to red. And this is actually the hue value. So according to the include angle between a vector and the red and the x-axis, this angle is called hue. Okay, this angle is called hue. And when the hue value is 0, that is red. When the hue value is equal to, for example, 45 degrees, that would be yellow. Okay, so this defines hue. And the saturation is defined as the distance between a color and the pure white. If the distance is larger, that means the color is more approach, is closer to the boundary. So we have pure color. Okay, for example, this point is pure red. This point is not so pure red, so that would be pink. Okay, because it's closer to the white. So the distance between the white and a specific color defines the saturation value. So how about the intensity? The intensity is the location in between black and white. So closer to white is higher intensity. Okay, so regarding hue and saturation, sometimes we just approximate this hexagon as a circle. Okay, just like this, we may usually see it as a circle and define the hue value and the saturation. And sometimes we also can view it as just simply as a triangle. So from red, yellow, green, cyan, blue, and magenta. And the intensity value is defined as the distance from a specific point to the black color or to the white color. And we can see that from this cube, we can slice a plane. Okay, so depending on the position of this plane, we define the intensity. Okay, so we can view the cone, approximate the cone as we can approximate the cube as a cone, like this. Okay, and if we view this cone from the top, we can see a circle like this, This is from this position, and we like a circle. We can see a circle like this, and this plane is from this position. And this plane has higher intensity because it's closer to the white, and this plane has relatively lower intensity. Okay, so this is the so-called HSI color space, and we may also describe it as a HSL or HLS. The L means luminous, is equal to intensity or brightness or value. Okay, so we may also call it HSV. V is stands for value. Okay, it's also indicating the strength of light. And we can also convert colors from RGB color space to HSI color space according to the formula here. And we can see that it's a little bit complicated because we have to transform RGB to a radius, okay, the include angle. Okay, so here it's more complicated. And intensity is basically the average of RGB. Another color model that decouple luminous and color information is the CMYK color space. And basically, this color space is constituted by three channels. The first one is L, that means luminous. A basically is the red-green contrast. B is basically the blue-yellow contrast. So we can use these three values to specify a color. And the LAB color space is designed to approximate human vision. So basically, we think that the LAB color space and the HSI color space is closer to human color interpretation. So usually in many multimedia systems, we prefer to use HSV or LAB color space to build a system more closer to human understanding. And actually, in addition to this color space, we have many other color space like YUV, YIQ, YCBCR. And YCBCR is widely used in video and image compression, such as MPEG and JPEG. And you can get more information from this web page. Just like an intensity histogram that can describe the distribution of intensity of gray level images, we can also use the color histogram to describe the distribution of different colors in an image. And basically the definition is the same. So we try to count the numbers of pixels with some specific color combination, so that we can construct a distribution describing the numbers of pixels with different colors. So here is an example. Given an image, we may count the numbers of pixels which red value is between 0 to 63, and the blue value is also between 0 to 63, and the total numbers of such pixels is 43. So here we can see in RGB color cube, we can count the numbers of pixels in a small grid. And the size of the grid depends on how we divided the color channel. For example, if we represent the red intensity by 256 labels, and we can roughly divide it into, for example, 4 ranges. So basically, we just count the numbers of pixels belonging to one of these 4 ranges. And also we do the same thing for the blue channel and as well as the green channel. So here is a 3-dimensional visualization of the color histogram. So given this image, we count the numbers of pixels belonging to each grid, and this is the so-called color histogram. And although this representation is very simple, but it's actually very effective in many multimedia analysis applications. So we will describe more in the future. And in previous slide, we quantized the, for example, the red color channel into 4 eco-space range. But actually, the human perception is not uniformly divided. We may be more sensitive to some specific color range. So actually, also there are some research working on non-uniform quantization. For example, for the hue from 22 degree to 45 degree, that would belong to the orange, and from the 45 degree to 70 degree, that would belong to yellow. But from 70 degree to 155 degree is all about green. So this is according to our human perception. So it would be better if we can non-uniformly divided the color range. Okay, so in this paper published in year 2003, they propose 3 different quantization scheme, and for example, for the achromatic range, if the illuminance is quite low, the value of hue is only quantized to 1 range, and the luminance is quantized into 4 range, and the saturation only 1 range. But with high chromatic, the luminance is only quantized into 1 range, and the hue value is quantized to 7 ranges. So still right now, there are still ongoing works on non-uniform quantization, and basically from many research works, they have demonstrated the effectiveness of non-uniform quantization. So the color histogram of an image represents the global statistic or the color distribution of pixels colors, and that has been demonstrated very effective in many multimedia analysis applications. And here we say that histogram is one of the most useful features to describe images or be the basis for similarity measure. For example, we can compare 2 images I1 and I2 based on the following simple calculation. Basically, we can calculate the difference between pairwise histogram. Okay. For example, here we calculate the difference between the ith bin, the value of the ith bin of the first histogram, and the ith bin of the second histogram, and we just sum all the difference to be the difference between 2 images. So this is one way. And because we can separately consider the distance between the distance from the perspective of red, green, and blue, if we use the RGB color space, and then we can jointly combine them to be the final distance between images. And in the future, we will introduce more distance measure or similarity measure between images. That will be the basic calculation for many applications. In the following, we will briefly introduce simple image features, and then basically we can describe images from many different perspectives. One of the most effective perspective is from the color. So based on color feature, we can construct color histogram, color moment, color coherence vectors, color correlogram, and many others. And the materials described in the following are mainly from the conference paper here. In addition to the color feature, we also will describe texture feature in the future. There are many types of texture features like Tamura feature, multi-resolution, simultaneous auto-regressive model, candy edge histogram, and so on. So first, the color moment is actually very simple. The color moment just contain only the dominant feature instead of storing the complete color distribution. So we can say that it's the so-called color moment is the very simplified version of color distribution, and we just store the first three moments of each color channel that are the average, variance, and skewness. So basically, these three values are simple statistical value, okay, given a distribution. So for example, we just calculate the average of red channel, variance of red channel, and skewness of red channel, and we can calculate the same values from green and blue color channels to form the color moments. So here are the formula to calculate the average, variance, and skewness. And basically, we say that average is the first color moment, variance is the second color moment, and skewness is the third color moment. And basically, these are all based on a simple calculation that has been taught in statistics. And when we describe images by color moment, how do we measure the distance between two images? That is also very simple. We just calculate the difference between average, difference between variance, and the difference between skewness, and then linearly combine them to form the final distance. And here, according to the importance of average, variance, and skewness, we may impose different weights to combine three types of difference. And usually, average value is the most important, and the variance is the second important. Another simple color feature is called color correlogram. A color correlogram expresses how the spatial correlation of parts of color change with distance. The main shortage of color feature is that the lack of spatial information. But how color distribute, spatially distribute in image would be an important information. For example, given an image, maybe the first half is black and the second half is white, and another image is that the first half is white and the second half is black. Then if we use the color histogram, two color histograms of these two images are exactly the same, but actually for human, these two images may be quite different. Okay, that is the shortage of color histogram. Okay, it lacks of spatial information. So color correlogram was proposed to describe the spatial information as well. So the histogram edge of an n by n image I is defined as this, and this is actually the same representation as we mentioned before. Basically, for each beam, we use it as a probability form, and n squared times this probability means the numbers of pixels belonging to this color grid. Okay, and the colors in I are quantized into C1 to Cm, and the notation P in ICI is synonymous with P in I, and IP equal to CI. And then the distance d be a fixed prior, and the correlogram of I is defined for I and j in M, k in d. The color correlogram R CICJ means the probability of pixel where one pixel is with color Ci, another pixel is with color Cj, and their spatial distance is equal to k. Okay, so this is the so-called color correlogram value, and in a word, this value gives the probability that a pixel at a distance k away from the given pixel is of the color Cj. Okay, so they not only describe the numbers of pixels with some specific color, they also describe the distance between two different colors. Okay, the spatial distance between two specific colors. Okay, and how do we define the spatial distance? So if one pixel is at x1, y1, and another pixel is at x2, y2, and the spatial distance is defined as this, so we just find the minimum of the horizontal distance and between the horizontal distance and the vertical distance. Okay, and this is the so-called color correlogram, and the autocorrelogram of I captures spatial correlation between identical colors. So if we specify spatially consider autocorrelogram, we means the spatial correlation between identical color. So here we count the probability. We calculate the probability of pixel with color C close to another pixel with color C with distance k, and this is the so-called autocorrelogram.